we're still out here on our
algebra detour.
Oh, by the way, dig the jingles? Special thanks to all the different artists in these episodes who have graciously written and recorded a little ditty for us. Check the description each time we're out here on a detour for their details. Anyway, we're still out here on our
algebra detour.
And I want to do a quick follow-up to last week's discussion. Remember that in a group, we want to have a binary operation on a set that needs to be associative, have an identity, and have inverses. But let's recall the specific definition. For instance, if dot is my binary operation and E is my identity element, condition number 2 in the definition says that we're required to have G dot E and E dot G both be G. But why both? That seems a bit overkill. If our motivating example to have in mind is Z, the integers, we're essentially saying that x plus 0 and 0 plus x are x. Why not just require one or the other? We already know that for any two integers, x plus y and y plus x are the same thing. The reason to require both is because in a group, there's no guarantee that g times h is the same as h times g. I mean, straight from the definition, it's nowhere to be found. But of course, if I just stop there and say, since it's not in the definition, it doesn't happen, I'm doing a grave disservice. Algebra's whole deal is that the definitions are straightforward, but hide all sorts of beautiful structure and results. So, just because there's no part of the definition of a group that says g times h equals h times g, doesn't mean that it might not happen regardless. Of course, it actually doesn't always happen regardless. That's the whole point I'm trying to make here. But I'm trying to make it seem like less of a given that it might not always happen regardless. Okay, so if I claim that in a group, g times h doesn't always equal h times g, then I've got to back up that claim. That's easy enough to do. I just have to give you an example of a group where there are two elements that have different products when you multiply them in different orders. And don't let last week fool you. Even though neither of the groups we unpacked then would work, neither z nor z mod nz, there are tons and tons and tons of groups that will. We can't walk without stepping on a group where g times h doesn't have to equal h times g. And here's one such example. It's the smallest example. Suppose we have a triangle like so. We're going to enumerate the vertices. 1, 2, 3, there we go. Now we're going to build a group where the set is all possible different enumerations on the vertices. So for instance, here 1, 2, 3 is one element of the group, and here 2, 3, 1 is another. It's a quick combinatorial exercise to see that there's only 6 elements in this entire group. There's only 6 ways to enumerate the vertices. You have 3 choices for the first number, 2 choices remaining for the second number, and the third number is then forced upon you, and 3 times 2 times 1 is 6. So that's the set. Now, for the binary operation, well, before I define it, let's first declare a default triangle enumeration. Let's say it's this one, 1, 2, 3. Now, I can think about any triangle enumeration in my group as a collection of movements on the default triangle that take me to my enumeration. So, for instance, if I have this enumeration, 2, 1, 3, well then, to go from the default triangle 1, 2, 3 to the triangle 2, 1, 3, I can first flip over this line that cuts through the vertex currently labeled 1, and then I can rotate counterclockwise once. So, another way to express this triangle 2, 1, 3 is that it's a flip followed by a rotation. And I can do this for all 6 triangles. Now, the binary operation is that if you hand me 2 triangles, or equivalently, 2 sequences of movements that go from the default triangle to 2 new triangles, then the third triangle that gets spit out by the binary operation is one where I start with the default triangle, then do the motions defined by your first triangle, and then, without resetting, do the motions defined by your second triangle. Now, I'm not saying to do whatever needs to be done to get to the second triangle. I'm saying do the motions that you would do to go from the default triangle to your second triangle. So let's see what I mean with an example. Let's say that we have the 2 triangles 2, 1, 3 and 2, 3, 1. And we want to compute 2, 1, 3 times 2, 3, 1. Well, we've already said that 2, 1, 3 is defined by a flip over this line followed by a counterclockwise rotation. So what are the motions that give us 2, 3, 1? Well, from the default triangle, I can rotate counterclockwise twice, and that gives me 2, 3, 1. Now, of course, I could just rotate clockwise once instead, but in a moment we're going to see it's easier to parse if I define all the motions in terms of flips over this line and counterclockwise rotations. So if I want to compute 2, 1, 3 times 2, 3, 1, then the binary operation is to take the default triangle and do a flip followed by a rotation, and then without resetting, do 2 more rotations. And subsequently, the triangle we get is this one, which is labeled 1, 3, 2. Great, we're halfway there. I'm supposed to be using this group as an example of one where g times h doesn't equal h times g, and these two triangles 2, 1, 3 and 2, 3, 1 are the g and the h I'm going to use to demonstrate that. So, we've just done g times h. All that's left is computing h times g, and fingers crossed we don't get 1, 3, 2 again. So if we swap the order and compute 2, 3, 1 times 2, 1, 3, then that means I take the default triangle and first do 2 rotations, then without resetting, we do a flip followed by 1 more rotation. And the triangle we get is this fella, labeled 3, 2, 1. And last I checked, that's not the same as 1, 3, 2. So, fantastic. Our work here is done. G times h doesn't always equal h times g. Well, sort of our work is done. I mean, initially all we set out to do was give such an example. But if we stop there, we're missing the bigger picture. Because, as we've already seen, sure, sometimes g times h isn't h times g, but sometimes it is, like in z, or z mod nz. This distinguishing feature is called being abelian, after Niels Henrik Abel, and not after Abel. That had certainly put a wild spin on Genesis, though. Am I my mathematician's keeper? But anyways, we say that a group is abelian if, for all g and h in it, g times h equals h times g, and non-abelian if it's, well, not abelian. You might also see a group called commutative if g times h equals h times g. That is, you can commute all g and h past one another. Mathematics has this habit of naming things in one of two ways, either after someone or descriptively. And there are actually pros and cons to both. I mean, the word abelian shows reverence to Abel, but it's not as evocative as what's actually happening, as commutative is. I mean, of course, that can also backfire. I mean, there's a billion things in math that are called regular or normal, so please stop giving that as your definition. Or you could show reverence to a mathematician that absolutely doesn't deserve it. How about you eat my shit and hair, Teichmuller? Where was I? Oh, yeah, abelian groups. So, this triangle group we just described isn't abelian. And this triangle group actually has a name. It's called the dihedral group of order 6. Order just means cardinality, or the number of elements. So this is the dihedral group with 6 elements. Which stands to reason there ought to be dihedral groups of other orders, and no surprise there are. The way you cook them up is by taking a regular n-gon, not necessarily the triangle anymore, and characterizing the elements of the group as all of the rigid movements you can do from a default numbering to a new numbering. I should point out that not every numbering is going to be valid. Just like with the triangle, you can actually boil down all the possible movements into flips and rotations. So, for instance, in the dihedral group of order 8, which is just the rigid motions on the square, vertex number 3 is always going to stay next to vertex number 4, and no rigid motion, no rotation or flip, is going to tear them apart. So, for instance, this isn't an element of the dihedral group of order 8, because it's not a valid way to enumerate the vertices of a square. Remember from last episode that when we were defining a group, we said that the idea of a binary operation in particular is motivated by the examples of adding or multiplying 2 real numbers and getting a third real number. It's therefore convention that when you're dealing with an abelian group, then the binary operation it usually has additive notation. What that means is that the operation is written with a plus sign, the identity element is 0, the inverse of g is minus g, and ng is g added to itself n times. That's not too surprising, because the groups that have honest-to-goodness addition as their binary operation, like z and z mod nz, are abelian. If the group in question isn't abelian, then we usually use multiplicative notation. So the operation there would be like dot, or times, or juxtaposition, or composing, or star, or so on. 1 is the identity, g inverse is g superscript minus 1, and g to the n is g multiplied by itself n times. Now, that convention might initially throw you for a loop, because multiplication of real numbers is also commutative. I mean, 4 times 5 is the same as 5 times 4, or else my first grade teacher has a lot of explaining to do. But there are multiplications that aren't commutative. The main example is matrix multiplication, if you're familiar with that from your linear algebra classes. And if not, I'm sure we'll get to it eventually when we start motivating homological algebra, so no worries. And then stuff like function composition definitely isn't commutative, and function composition is basically the operation we're doing with these dihedral groups. Just like how in topology, we've been building up a list of topological properties to be able to characterize topological spaces, we can do the same with groups, even though this is currently just a
algebra detour.
Not a full-fledged algebra expedition. Here, being abelian, or not, is an algebraic property of groups, and so we can tell two groups apart if one is abelian and one isn't. Of course, that begs the question, what does it even mean for two groups to be the same in the first place? With topological spaces, the idea is a homomorphism, which was a bijection on the underlying sets that was able to carry the topological information back and forth. And remember, since carrying topological information is the quick punchline for what a continuous map is, a homomorphism is just a continuous bijection with a continuous inverse. So a group equivalence ought to be something similar. It ought to be a bijection on the underlying sets that carries the group information back and forth. So, to answer when are two groups the same, we first need to answer, what does it mean for a map to carry group information? Well, in topology, a continuous map is one that takes pre-images of open sets to open sets, because that's the way to guarantee that the three axioms of a topology are satisfied. Topologies are defined in terms of open sets, and continuous maps respect the open set structure. Now, with a group, the structure isn't open sets, but instead this binary operation. So a group map, or a group homomorphism, is a function that needs to respect the binary operation. And the way to do that is to require that whether I do my binary operation first and then the function, or I do the function first and then the binary operation on the images, I should get the same result. In other words, if G1 and G2 are any two elements of a group G with binary operation dot, and H is another group with binary operation star, using two different symbols just to tell them apart, then a function f from G to H is a group homomorphism if f of G1 dot G2 is equal to f of G1 star f of G2. This is exactly what it means for the map f to respect the group operation. And of course now it becomes very easy to say when two groups are the same. Just like a homeomorphism is a continuous bijection with a continuous inverse, we say that a group isomorphism is a group homomorphism bijection with a group homomorphism inverse. We say that two groups are isomorphic if an isomorphism exists between them, and this is the right notion of what it means for two groups to be the same. Now, it's a slippery point, but one that crops up a hell of a lot in future contexts, so it's worth internalizing now. But an isomorphism isn't an equality, even though we tend to get a little sloppy when we talk about it and just off the cuff say that the groups are the same. Two groups literally being equal only happens, well, when they're equal. That means that the sets are literally the same set, and the binary operations are literally the same. But you could have an isomorphism where the groups aren't literally equal. Here's an example. Consider a set of three elements, A, B, and C. We'll cook up a group whose elements are permutations of A, B, and C. That just means that the elements of the group are bijections from the set A, B, C to itself. And the group operation is function composition. This group is called S3, the symmetric group on three elements. Feel free to check for yourself that it satisfies the definition of a group, but as we'll maybe see in a few weeks, it very much has to, because it is the prototypical example of a group. Now, it's not equal to the dihedral group of order 6. It can't be. The underlying sets are literally different. One is these enumerated triangles, and the other is bijections from ABC to ABC. But your homework is to show that these groups are isomorphic. Since we don't have any machinery under our belts yet to easily show when two groups might be isomorphic, the best way you have to tackle this homework is to do it by brute force. Each group only has 6 elements, so it's not too difficult to cook up a function by hand, which sends each enumerated triangle to its quote-unquote corresponding permutation. Hint for you, to get a grip on the two binary operations, it's actually super helpful to draw a multiplication table for each group, like you might have when you were learning your times tables in elementary school. What that'll do is it'll get you comfortable with all the elements in each group and how they multiply together to give it different elements. That's essentially the entire structure of the group. So from there, it's not too tough to cook up a group homomorphism that has an inverse group homomorphism. And I should definitely point out that this approach really doesn't scale. As soon as your groups get larger, or let alone infinite, writing out the complete times tables and using them to dream up a potential isomorphism becomes a Sisyphean task. Good luck, have fun. Oh, and one other thing to point out, we just defined S3, the symmetric group, on 3 elements. And of course you can define Sn, the permutations on n elements, in the same way. Or even permutations on a set of infinitely many elements, that's okay too. Although, a quick warning, it's not true that any more of the dihedral groups will be isomorphic to any of the symmetric groups. It's very much false, except for your homework question. So, for bonus points, give a reason why Sn isn't isomorphic to any dihedral group if n is bigger than 3. And we can actually do that with just the terms defined today. Or, if that's a bit intractable right now, just explain why S4 isn't isomorphic to the dihedral group of order 8, the rigid motions on the square. Thanks for joining us on this
Algebra detour.
once again. Next time we'll talk about group presentations, which are a handy way to write down groups, and the reason I can be so confident in saying that dihedral groups are just generated by flips and spins. See you then!